Okay, let's see if we can make sense of this. That is a pulsed red laser. Okay, so the red laser is here, pulse, pulse, pulse. Now I'm going to show you it accelerating as it gets pulled through a venturi. Okay, so let's see that. Light disc sucked through the venturi. Now, so we saw the pulse, pulse, pulse. Now we are seeing the actual particle itself. You see this? It's pulling itself right out of its wave because it has to accelerate to go through the venturi. This is fully understood. Gas cars used to use this in their carburetors. It's a venturi effect. Now, here's what happens, and I will show you this in extreme close detail. Rod Warren and I worked on this years ago, and it's pretty interesting. Now, so we have the light accelerating. We have the light concussing here. Now, you're seeing an extreme white glow here. Okay? And then you're seeing these. They call that interference patterns. Well, they're not interference patterns. They're repulsion patterns because the white always wants to push away from the other whites. It hates the other white guys. But the little black balls will be all around here. Normally, when that came in, when this light accelerated, it's a box of particles like this. That's a photon. And when it hit here, the explosive part blew up, and the little black balls, as I will show you, just rolled away. Let's see that. All right, now don't forget, here we are at the venturi, and I'm saying these little black balls you see all over the place were normally attached to these particles, and now they have walked away. See the little black dots? And they don't mind being against each other. They'll lay right on top of each other. They have no problem doing that. The white ones hate each other and they want to stay away. Look, they're just hanging around. They have globs of them here and there. I believe those are the black balls of gravity, and they will always want to seek the white balls. Now, there does appear to be a discrepancy between the number of blacks and white balls, because that's what they call lepton universality, and it does not seem to be equal. Or, I don't know what to say about that. I'm going to stay away from that. But I can see they're separating. There's no question whatsoever. The black ball is working away from the white ball. Let me show you the particle in its totalness. All right, here, remember again, red pulse laser accelerating and then splitting in the venturi. That's the venturi right there. Coming back this way, we see the actual particles. You see that? Black and white, just like this. And then I showed you, or I will show you, the black ones separating from the white ones. That's extreme energetic reaction. Now, there may be some way of taking advantage of that right after the venturi in this distance here. Maybe there's going to be some special absorption factor. I don't know. I have no idea. But I can tell you what, there's an extreme amount of interaction at and surrounding the venturi. Okay, my friends, I'm going to try to take a rational attitude at this. I am very upset that they won't listen. They understand about neutrinos and leptons breaking the speed of light. And this is about the time that Rod and I started to put this information out. Then the Royal Institute a year ago puts out the standard model. Here's how the standard model works, which is Niels Bohr. 1913, he comes up with a standard model. Einstein says, oh, if that's the standard model, then here's how light works and here's all the rest of the stuff. Nothing was right from the day one. The standard model is wrong. The speed of light is nonsense. You can go faster, slower, doesn't mean anything. Light is a particle. Light itself divides. Light itself becomes two, at least, electrons, and the electrons will kill you. The photons, like that's a photon, that won't kill you. That will kill you. These go through the air. These just go flying through the air, banging and bouncing off of other particles to make light. These invade other matter and explode it and burn it and sizzle it and destroy it. And it's time to pay attention to what the reality is. They now know. Look, could the standard model be wrong? Absolutely it's wrong. No question it's wrong. Here's what she says right here.
Good. Well, what that means is that there's something wrong with the standard model. We found the crack, finally, in our understanding of particle physics. There's absolutely no way that we can explain this observation with our current understanding.
And this is the observation that Rod Warren and I have been putting out for several years. Now, they just admitted this back in December of 2019, so that's about 6 months ago or so. Now, then they go into why is there more matter than antimatter in the universe. And this is where it splits between the black and the red. And I will show you that. Well, black and white, actually. It's not just the Royal Institution. Here's another one saying, the new boson appears in nuclear decay, breaks standard model. Nuclear decay is nothing more than eventually ending up with light. You have big chunks of particles that are mass, and they slam into each other, and the little tiny bits of particles end up being given off as light, and they can finally see it. Weird electron positrons, decaying beryllium and helium hint at a new boson. Well, that's because they keep getting down smaller and smaller and smaller. We started with light, so we split light. You see that? That's light. This is light right here. These are photons. And as they approach the Venturi and explode and divide from black and white, they start to display themselves. And they will do that in green and blue and the different colors. And the reason is because they're less and less attached to the nucleus. The nucleus is a ball of electrons, just as well as these are electrons. But these end up going into resonance static, stable quantities. And it's 1837 in a proton, 1838 in a neutron. Just use that to calculate out how big the nucleus is. So if there's, like helium is, I think it's 7,350 electrons in the core. Now, helium only has just right close particles. But in your bigger ones, they get out more and more shells around it, and the less and less close are red and green and blue and so forth as they go away. Now, we're going to get into all this, but get your book and make sure you're writing all this stuff down so you can go back to it. All right, now I'll show you the green is the same. All right, this is the green, and once again, the green is much more powerful. So the red started to show up around here and exploded at the Venturi. These start to show up way back here, and then they get brighter and brighter as they explode in the Venturi, and then they separate the blacks from the whites, like I showed you in the bosons. All right, all I can tell you is that is light. Okay, that will not kill you when it hits you. You know, it's concentrated, it could burn you. But it's a box of particles. That's, to me, is what we would call positive, because a negative is what we call the electron. And this is the electron, that's the boson. Or you could call that this is the muon neutrino, and this is the electron neutrino. This has explosive power. This has nothing. I showed you before, when they hit, the white explodes like a bomb, the black walks away. Well, I'm going to tell you what, right there, half of these, that's electricity. That is electricity. This will kill you. When they're banged up together, side by, you know, in like a bar magnet type of a configuration, they will not kill you because they will not incorporate into the material. They will bounce off that material and create light because they're already complete. Once they're not complete and they are in an electron configuration, they will flow or they will invade. If they flow, it's through copper or it's through something that has an extreme amount of conductivity. If they invade, it is through something that is like organic matter or your body or something. And then they explode and light up and burn and sizzle. Well, they don't burn and sizzle going through copper wires because there's a ton of extra electrons. Now, just in case you haven't picked up on electron flood theory, it says that there's nothing more than electrons in the nucleus. But electrons are not just negatives. An electron is a strong force and a weak force. The weak force is the black ball has no energy whatsoever. It's just a carrier of the strong force. The strong force is extremely concussive and explodes into a huge shower of particles, and the black ball just rolls away. Photons are back-to-back electrons. There might be 2 or there might be 4. I'm not positive. Now, electrons at rest, which is heat. Heat is electrons. The more heat in a mass, the more electrons are just floating around in there, pushing other ones apart. That creates heat. Now, once you get into the extreme quantities discharging, that is electrical discharge. That kills you. Heat does not kill you, it just warms the hell out of you. It depends on how much you're flushing in. How many electrons are you throwing at me? You know you can heat up quick, you know you can heat up slow. It's the number of electrons you're throwing at you. It's an interaction of the magnetic fields of that tiny little particle. These fields are way out here, and when you bang into them, it creates heat, just the way it works. Just so we get on a right page here, this is just the light coming from a red pulse laser. And then we go through the Venturi. This is light sucked through the Venturi. You see it here? There's the waves that we had before, but now the particle itself, which is light as a particle, is being pulled out of the wave and concussing at the Venturi, and there it splits into the black and the white. And now this is the one that's really interesting. All right, and these are the white spinners, and the black balls go around everything. So now we see them as the white spray coming down, and then they start to reform. But there's one of those white particles. You see it? It's exactly what I showed you with the red discs, only that's a white one. Now, the red has much less energy than the green or the blue, because they, in my mind, are further out around the nucleus. And the nucleus, again, is not one big positive mass. It's a dipole. It's got positive and negative. And that's what attracts the negativeness into the positiveness. I say the positiveness of these molecules, or these atoms, is gravitational pull. As they get bigger and bigger, they pull harder and harder. Simple as that. And they have no concussive value whatsoever. None. 0. They just turn into little black balls amongst the white brilliant light. Now that created what I will show you in a second. Okay, my friends, this is going to get a little tricky, so pay close attention. You see all these little particles here? They're all little circles around black balls. You see that? Black ball everywhere. And there's circles around them, every one of them. And then even out here. Now, what is this? That is an extremely energetic region. What does that mean, Roger? Well, I'm not sure. But here's what I think is going on. Again, Rod did the work on this, so I believe the laser is coming this way, and he's got it askew so that it is impacting here and bouncing just a smidge off this way. And he's picked up a reverse spinner. Now, why do you say that, Roger? Well, because I have seen another one that was a reverse spinner that I'm almost certain of, because it created the most strange event, and I will show you that now. But don't forget, why is this one bright? Nothing else here is bright, not a single one. Why is that? Well, let's see if we can figure it out. Now, I believe that was the particle that we saw as the white particle amongst the disks, and then you can see it's pretty obvious it's concussing with one of the normal showered electron disks, and it's creating this. Now, the brighter the brightness, the more energy. All right? These are coming obviously this way. That's the energetic impact, energetic impact, energetic impact. Now, what is this doing? What was this before it hit this? We got some thinking to do, Lucy.